Hi everyone, my name is Daniel Lehovic and I work in the Competence Center Woodcape, which is located near one of the most beautiful European cities, which is Vienna. Today I would like to briefly present to you what I do in my research and some of the first results. The topic of my presentation is dynamic compensation of load sphere response for cutting force measurements in wood machining. Enjoy! Cutting tools produce a cyclic impact of the cutting edge on the workpiece, what results in dynamic excitations leading the measuring system to vibrate. The consequence is a strong alteration of the force signal, and this is why, to be able to provide interpretation of this data, some kind of filtering, which takes into consideration setup's dynamic properties, is needed. The reliable cutting force measuring method is of utmost importance for tool and process optimization. One of the most common methods of direct cutting force acquisition is by means of piezoelectric force sensors. When force is applied to the sensor, the quartz crystals generate an electrostatic charge proportional to the input force. However, the main drawback of these sensors is that they usually express high distortion in measured signals, as cutting frequencies approach the transducer's resonant frequency. The whole problem can be overcome by means of model testing, which is a way of examining structural dynamics of a given object. Let's see an example. The first step of model testing is excitation of the system, and this is the result. In the following figure, the red curve represents an impact or excitation, and the blue one a response of the measuring device. As you can easily notice, these figures are not the same. However, this free vibration is the natural response of a structure to some impact or displacement, and is completely determined by the properties of the structure. To visualize it easier, imagine a guitar. When you pluck a string of the guitar, it vibrates at the tuned frequency and then generates sound. According to the datasheet, the usable frequency range of the force sensor we used is just 1/5 of its first natural frequency, which is way too low for dynamic measurements. When this range is exceeded, then dynamic compensation has to be applied. For instance, when we are out of this region, at resonant frequency for example, it means that what we observe is for example 1 kilonewton, when in fact it is 100 newtons, what leads to overmeasures and financial losses. Correction process consists of multiplying measured forces transformed to frequency domain by the inverse of the frequency response of the system, which had been previously obtained by means of model testing. The final result is marked with green in the shown figure. As you can see, its input to output ratio is now equal to 1. To confirm these theoretical assumptions and see how this phenomenon affects measured data, simple experiment was carried out. The self-developed test setup that was used during the experiment enables analysis of these integration processes at cutting speeds up to 80 meters per second. The specimen, which is mounted on the rotating arm, passes the stationary knife where cutting process occurs. The design of experiment included one wood species, one chip thickness of 200 microns, and 8 cutting speeds ranging from 10 to 80 meters per second. In the following figure, you can see one random cut for both unfiltered and filtered signals. The shape of the curve can be explained by the arrangement of the workpiece used for the test. The workpiece consisted of 2 polyurethane blocks between the proper sample, which were designed to partially dampen the initial impact. By means of aforementioned inverse filtering method, we managed to get rid of unwanted oscillations. As you can see, there is also significant change not only in the shape of the curve, but also in its value, what indicates that the problem of dynamically induced errors cannot be neglected. As far as calculation of the average cutting force in both cases is concerned, 2 basic approaches were used. The first one included the calculation of the arithmetic mean from the range corresponding to wood only, which is marked in the shown graph with dark blue and dark red. Within the second approach, we focused on measuring peak forces, as these forces were the most interesting to tool manufacturers that we cooperate with. The results are as follows. In case of peak forces, the values for the unfiltered signal were significantly higher, which was not surprising given the oscillations shown in the previous slides. Although trends seem to be similar, it is worth mentioning the slope at 60 meters per second. This phenomenon may be related to the resonance of the measuring device. Distinct results were obtained for the second approach. In addition to the smaller values, the force distribution for unfiltered signal has also changed. The minimum value was now observed for 20 meters per second. What is the most interesting here is that the values are almost identical for both cases. The only differences are in standard deviations, which were much higher for the variant in which no filter was used. The obtained results can be explained by the fact that, as a consequence of using a filter, a portion of the signal, which was affected by the resonance of the measuring device, was compensated.